I'm a technical evangelist at AWS, but enough said about me. What we're going to talk about today is basically I want to share with you some. So we switched from the database world to the architectural world and the way you can design modern architectures using kind of new patterns in a serverless fashion. So I have a brief introduction about what serverless means, but let me ask you, how many of you have experienced or have prototyped or have built something in production with serverless already on any platform? Not too many. Good. So this is useful for everybody, hopefully. So the way we think about serverless is it's not that the server disappears. There is always a server in there somewhere processing your workload or handling your API requests. A lot of people are confused by this buzzword of serverless. Of course, there is a server. And what I want to share with you today are 4 categories of architectures that you can build in the cloud. And hopefully these are reusable, and these best practices and ideas and architectures may apply to other platforms as well. So if you're not on AWS, don't worry. I think you will learn something anyway. This was already said about me. I come from a startup world. I'm a developer, I think, like most of you. How many of you are a developer today? I guess a lot of you. Great. So I'm a developer as well. I organize some events around the world. They are called Serverless Days, and I've been using, as a customer, AWS for 4 or 5 years, and then I joined the company last year. So today I want to share with you a bit of my experience and a bit of other ideas about serverless architecture. So this is the agenda. I have a very brief introduction and fundamentals about serverless for you. If you have never used it, if you're not too familiar with all the concepts, and I will be talking mostly about AWS Lambda and our function as a service offering called AWS Lambda, but I think, again, most of the ideas apply to other FaaS as well. And then I have 4 categories of patterns or architectural patterns. So we'll go through each and every one of them, specifically web services and stream processing, usually real-time data processing, and then data lakes and machine learning. So these are 4 big categories. We could talk like an hour about each and every one of them, but I have roughly 10 minutes for each. So if you have questions about any of these specific categories or patterns that we're going to see, just I'll try to leave some time for a Q&A, or you'll find me on social media or afterwards later today. So let's get started. This is, roughly speaking, the spectrum of compute that we see at AWS and that we offer at AWS. And I call it a spectrum, even though there are like 3 separated different categories there, because I want to clarify what actually serverless means. So we have the first category on your left, which is what we consider everything running on bare instances. Okay, we call it running on EC2, our Elastic Compute Cloud service. And in there, you can run whatever you want. Okay, you spin up a server, you install your stuff on it, your dependencies, your projects, your codes, and then you do whatever you want to do. And that's the opposite of serverless. You have to take care of the servers, you have to patch it, you have to maintain it. You probably have a system operations team or a DevOps team in your organization that's taking care of that. There is a section in the middle that we call this section managed services, and actually some of the services are both in the managed and in the serverless section, because depending on how you use them, you may see and use them more in a serverless way. So these services are managed, meaning you don't have to take care of all the heavy lifting of operating, maybe a MySQL cluster or maybe an Elasticsearch cluster, but still the cluster concept, the server concept is there. Okay, so you have to decide how many servers, you have to auto-scale it if you want to, if you have flexible, if you want to achieve elasticity, and you have to take care of these servers, maybe patch, update the versioning, or even sometimes SSH into the actual machine and do something with it. So it's managed, not really considered serverless. So everything about Neptune and graph databases and MQ and Redshift, Elasticsearch, Elasticache. Like these services give you a lot of functionalities, but most people do not consider these serverless. And then we have, on the right side, the actual serverless offerings, services. The first one is AWS Lambda, because that's the compute part, so that instead of uploading your code or injecting your code into a machine, an instance, or a container, all you provide is a little function. That's why it's function as a service. And then we take care of all the scaling. And then there is a whole range of services around it. They give you authentication and analytics and data ingestion and monitoring and tracing and queues and databases. So you can be serverless in 100%. And let me tell you what are the main advantages of this approach, because if you come from a server full world, maybe it's not particularly intuitive. The idea that you provide your code and we take care of all the heavy lifting under the hood means that the scaling is completely flexible, first of all. So we take care of scaling your workload horizontally. So when there are new requests, we make sure there are new runtimes or new containers or new whatever. We take care of that handle your load. And this works, if you need 1 million concurrent requests, no problem, we take care of that. But if you have an infrequent kind of workload, or maybe you are a startup and you are just prototyping, or you have a new feature and nobody is using that feature yet, although it's deployed in production, well, this flexible scaling also goes down to 0. Okay, so we call that no idle. You never pay for idle with serverless. So that as long as there is no traffic, no requests, nothing going on, you're paying basically 0. So I think that's a very good value proposition. So you can optimize for cost or prototype new features quickly and cheaply, because nobody using it, you pay 0. The other advantage is that since we take care of all the infrastructure, operations, networking, auto-scaling, it means we can take care of all the high availability and resilience of the architecture at the below the application layer, and that comes with advantages. For example, we make sure that we deploy your code, your application, into multiple data centers, multiple availability zones within an AWS region. That's how we call them. So that even if a whole data center goes down for any reason, your app is still up and running. So I think this is a pretty good advantage. And you can do this with EC2, you can do this with traditional instances, but you have to have that expertise and you have to operate the system in the mid-long term. So as a developer, this takes a lot of heavy lifting off of my workload. I write code, upload it, and then I get some metrics and I make my customers, my users happy. That's why I want to write code in the first place. This is what the execution lifecycle of AWS Lambda looks like. And there is a concept that we call cold start. And these cold starts happen whenever it's the first time or it's been a while since you invoked your function, maybe earlier today or yesterday. So if you have a very infrequent kind of load, you can expect to have this kind of cold start, because there are a few things that need to happen, like we have to download your code, start a new, it's not really a container, but think of it as a runtime where we have already a set of libraries and we inject your code in it. And once everything is ready, we can finally execute your code, okay? But this requires some cold start time. When you talk about resources in your functions, okay, it's not an instance, but you can still kind of tune the CPU, the memory, the networking capabilities. And there is one handle, actually, and I call that handle power, although you will see that handle as a memory, as a RAM handle. So you can go from 128 megabytes up to 3 gigabytes. Okay, depending on the power that you give to your functions, you will have more CPU, more memory, more networking capabilities as well. So if you are CPU bound, memory bound, or network bound, you might experience that giving more power will be actually faster. And the best thing of serverless and function as a service is that if you can be faster, you can be cheaper as well, because you are charged not by the hour, not by the month, not by the day. You're charged by the 100 milliseconds execution time. That's why we can go down to 0 cost if there is 0 invocations. So if your code is running for 250 milliseconds, you will be charged 300 milliseconds. If you run for 301, you will be charged 400. Okay, it's really important with serverless and functional service, like optimizing your code can have a pretty significant impact on the performance and the cost of your solution. So for example, back to the example, if you're running for 301 milliseconds, we are charged for 400. If we can reduce and optimize the performance for even 2, 3, 5 milliseconds, we will pay 300. So we save 25% of our cost by optimizing 3 milliseconds of code execution. So like having a good visibility over the metrics and what can be optimized can really change the game. There is a good way to avoid guesstimating. So this power handle sometimes a bit not super intuitive. So I've built a project a couple of years ago when I was still a customer that allows you to basically fine-tune the performance and the power of your functions in a data-driven way. So what I'm doing here, I have defined a state machine using another service called AWS Step Functions. And this state machine will take your function as an input parameter and will run it with multiple power and memory configurations, will gather enough statistically relevant data, and then it will come up with an optimal configuration. Okay? And I've seen some customers using this approach even in their continuous integration, continuous delivery pipeline. So whenever they have a new function or a new version of the code of that function, they can run this and then deploy the optimized resource allocation for that specific function. So you can be very data-driven. You don't have to really guesstimate, really. A few best practices. These are especially valid if you're programming in Java, actually. So I hope most of you will benefit from this. Some of these also apply for Python or Node. It's really important to remember you can run basically any programming language on AWS Lambda today. If you asked me 6 months ago, I would have told you, okay, Node and Go and .NET and Java and Python, different versions of different programming languages. Now you can bring your own custom runtimes, meaning every programming language can run on Lambda. We have customers and partners using COBOL on Lambda, like migrating mainframe code to Lambda. So that sounds weird and scary, but it means you don't have to maintain a hardware of a mainframe, and you can run it in parallel as many times as you want. So that's a real life changer for these companies. So when we talk about optimizing your functions for cost and for performance, you should try to minimize the amount of dependencies, and especially in the Java world, a lot of the web frameworks have been built over the last 10, 15, 20 years with the idea of a running server that might take 30 seconds to spin up. That's totally fine in the serverful world, but if the same initialization static code, if you want to run it on Lambda, it means you have probably 5 or 6 seconds of cold start, and you want to avoid that. So my suggestion is try to separate dependency, try to use minimal, very lightweight libraries that give you dependency injection or data mapping, data binding, or ORM and stuff like that. It's not that you cannot use them, but if you can use a minimal version of it, you will see that the amount of code and the amount of dependency will go down and the performance will be better. You can use all sorts of other tools, like try to use environment variables to personalize and customize the behavior of your functions. So if you have a dev, stage, and prod environments, do not hard code credentials, do not hard code custom behavior based on the environment. You can inject different logics using environment variables. And if you really need to centralize those secrets, those passwords, those environment variables, you can externalize them into another service, maybe the parameter store, for example, which is a free service that everybody can use, or maybe the AWS Secrets Manager that will even automatically rotate the passwords of your databases transparently from your application layer. So pretty cool. There is another side of things that is, how you deploy and how you even simulate locally this new serverless world. And you can use AWS Sam, the serverless application model, which comes also with a local open source CLI tool that allows you to emulate Lambda and API gateway and some of the other services and tools that you probably want to run in local before you deploy them to production or to a dev or stage environment. So basically, Sam is an extension of a tool that we have, which is AWS CloudFormation, which allows you to do infrastructure as code. And so you have a template for your applications, and you can deploy that template to multiple accounts, multiple environments, multiple regions. So it's very easy to deploy, very easy to replicate. There is another area, especially in the CI/CD world, continuous integration, continuous delivery, that allows you to automate the process of building dependencies and creating the artifact and running tests and then deploying your stuff to either an instance, a container, or a serverless function. And we call this the code suite. There is code pipeline, code commit, code build, and code deploy. These services allow you to build that sort of pipeline. If it's a lot to get started with, and it is, I think, you can get started with another service above them, which is called Codestar, which will kind of bring you all of this package and a lot of good defaults to get started quickly. It gives you a dashboard, gives you a CI/CD pipeline. You just git push, and your code is updated in a few seconds. So it's pretty convenient to get started with. OK, enough theory. This was the fundamentals concepts. I'm sure it's not 100% clear. So if you have questions about this specifically, please raise it later at the end of the session or ask me later. We could talk about Lambda itself and the best practices for like an hour. Let's get into the architectural patterns and categories that I mentioned. So let's start with web applications. This is the typical starting point for most web applications. Let's call them modern web applications, where you have a top tier of front-end or client-side stuff, like static websites or assets and images and JavaScript and CSS. And what happens there is that if you separate your front end from your backend really, really well, it means your front end can be static, and you don't need any server code execution at all. And it means you can put this stuff into S3, our object storage, and deliver that worldwide using a CDN, because it's static content. It can be cached in our 150+ edge locations around the world. So that's the static part, and you can handle authentication, authorization, maybe with Amazon Cognito and other services, user management, emails, signups, password forgotten, like this stuff that you don't want to re-implement for the 10th time in your life. You can delegate all of that to Cognito. And then on the bottom side, you have the typical backend, where you have an API layer, you have a compute layer, which in our case is Lambda, and maybe you have a database, because otherwise, what are we doing here? Without data, the web would be very boring. So here I'm using DynamoDB, Amazon DynamoDB, but it could be an RDS instance, it could be SQL, it could be NoSQL, it could be a graph database, it could be Elastic, it could be Redis or any other sort of data source. Let's talk about Dynamo, because I think for serverless, it's a very good fit, because now you can scale down to 0 with on-demand capacity, and you don't really have to do capacity planning or provisioning at all. So it's a very serverless-friendly database, let's say. But this is the starting point. Let's see how we can tune it to add more features, to add more power to your web applications. So to talk about that, we need to talk about let's talk quickly about the API gateway part of things. So API gateway gives you a RESTful interface on top of your Lambda function. So you define endpoints and methods like get, post, put, and you say when there is a slash my feature get request, invoke this Lambda function. When there is a post request, invoke this other Lambda function, or the same. That's up to you. API Gateway comes with a few different endpoint types, we call them. The first one that we released in 2016 is the edge-optimized endpoint type. Edge-optimized because it's meant to be a globally distributed endpoint type, optimized for latency for everybody. So if you have your Lambda functions in Dublin, in the Dublin region, but you have customers and users and clients in Australia, you don't want them to go all the way through the internet to reach your API. So the edge-optimized endpoint allows your customers around the world to enter the AWS network as close as possible to where they are, and then we route their request to your Dublin region, for example. So there is, inside the this endpoint, we take care of the CDN side of things, of the cloud front distribution, and we route the request to API gateway. There is a way to kind of improve what we have done in the previous architecture, which is, if you remember, we had a cloud front distribution only for the front end, but sometimes you want to cache also the APIs, or you want to add some custom behavior to your APIs at the edge. So a way to improve that would be to bring the CloudFront distribution also in front of your API gateway. That is possible. This allows you to use all the edge services. For example, you can use Route 53 or the web application firewall to protect your APIs, or you can use Lambda Touch. Lambda Touch is basically mapped to your CloudFront distribution, and you can run code, AWS Lambda code, not in the data center, not in the AWS region, but at the edge location directly, so as close as possible to your user. And these Lambda Touch functions can manipulate headers, or change the transform or change or manipulate the content of the request or the response, so that you can do A/B testing, cookie management, authorization at the edge, and all these interesting features. For example, there is a customer that's using this. For example, if the client requesting an image supports WebP, with Lambda Touch, they will transform the JPEG image into WebP, so they minimize the latency, and then they minimize the network traffic using a more optimized version of that image. But not every client supports it, so they want to do it at the edge, not in the server directly. And everything you do with Lambda Touch is completely transparent to the rest of the architecture. So it gives you a nice extensibility. Maybe the backend is not the responsibility of your team, or maybe the backend is like a legacy system, and you want to add new features and new advanced stuff with Lambda Touch. So it's pretty powerful. There is a second API endpoint that we call regional endpoint. So this is not optimized for a global audience. This is optimized for an audience or a target client set, which is regional in a specific AWS region. Okay, so you create an API endpoint in Dublin or Frankfurt or Virginia or Tokyo or Sydney, wherever you need it. And this has the advantage of being cheaper than a global one, because there is no CloudFront distribution. And if you, for example, if you are invoking your API from an internal service, so it's not for your customers or for your global clients, but it's for a regional service deployed on EC2 or deployed within an AWS region, and you are invoking this API only from there, there is no point in going out on the internet, using a CDN, and then going back to your API. So you can use a regional endpoint for that. Or even better, you can do stuff like this. So you can build something that we call multi-region architectures, and you may want to have the same identical AWS stack on 2 different regions. So I think it could be, I don't know, Ireland and Germany, or it could be France and United States, depending on where your customers are. And you may want to do this for redundancy, to improve availability and resiliency, because maybe some dependency in this region goes down for any region, for any reason, and what you want to do is you want to fall back all the traffic to the other region, which is still up and running. So this is called disaster recovery, let's say. And it is super convenient with serverless, because if you're doing it for disaster recovery, so you're using the first region 100% of the time, and the second one only when there is a problem. The second one is costing you nothing, because serverless, again, if nobody is using it, you pay 0. So this is super convenient in the serverless world to go multi-region and to improve the resiliency of your apps. There is another way to do that, which is if you add in Route 53, this other service here, you can even do stuff like latency-based routing. So you can tell Route 53, hey, route my users to this region or to the other region based on which is closer to the final user. So you can also use both regions at the same time, not for disaster recovery, but for improving latency and improving the user experience. And you can always bring in another CloudFront distribution and Lambda at edge and all the other edge functionalities that we already discussed. There is a third API endpoint that we call private. Okay, so the private endpoints are not reachable from the internet. and you map them to a specific AWS VPC. It's like a private network inside your cloud. And you can even map your VPC with your on-premises data center, for example. So it gives you an opportunity to invoke your private API gateway endpoint backed by Lambda and Dynamo and whatever from your on-premises data center. So why not? It's super powerful to do legacy system integration or to provide a scalable API endpoint to older systems, for example. OK, let's go back to the typical web app. And let's talk about security for a second. So first of all, you want your endpoints to be secure. You want your content to be delivered through HTTPS. And that's something that CloudFront does for you. If you enable and force HTTPS, you can even map a free certificate using Amazon Certificate Manager. And that's another free service that does everything for you. It even renews the certificate when it expires. So there is no situation anymore where you go to a website and it tells you, no, the certificate expired, the website is down for a week now because they need to renew it. So that's a good advantage. And CloudFront itself gives you other features about security like geo-restriction. You can assign URL to restrict access only to specific users, maybe the ones that subscribe to your service or things like that. And DDoS protection. So since we own the global network, we can protect all the services inside the network at the edge with DDoS protection. And you can even implement your own web application firewall at the edge. And there are rules for like SQL injection or any other stuff that you can block even before it reaches your APIs and your Lambdas. Well, S3 itself, it gives you very powerful ACL controls and bucket policies to make sure only the authorized users can read your stuff on S3. Well, if it's a public website, static public website, probably everybody can read everything. But if you want to have there some configuration or some stuff that's not open to the public, you can handle that, of course. When it comes to authorization and API management, well, API Gateway gives you all the cross-account functionalities. So if you want to centralize some authentication logic, for example, you can do that. Or if you want to do special throttling or monitoring or rate limiting per endpoint or even per method. So you can rate limit the get differently from the post method, for example. Or you have usage plans. So you can map API keys to your usage plans and give it to different tiers of users so they have a different rate limiting and throttling and so on. Lambda, well, by default, your Lambda functions have permissions to do nothing because that's security by default. So if you want your functions to read from a database or to write into a queue or to really do anything with any other service, you need to provide permissions for it. And I think that's a pretty good default. And we call them function policies. So for example, you can say this function can only write but not read from this DynamoDB table. Or another case, this function can only read from this specific table, only this specific column, and not all the others, because that's your use case. So you can have very, very granular permission. And the best practice here is give the least amount of permissions, the least privilege approach to your function. So if anything is leaked or if anything goes wrong and you have code injection or other vulnerabilities in your dependencies, you can make sure that function cannot go around and break stuff or read secret stuff in your environment. Well, Dynamo itself, you have encryption, you have VPC endpoints if you want it to be read only from a VPC. Or again, it gives you very granular permissions for read and write only specific tables or rows. And when it comes to authorization, well, you can even implement what we call a Lambda or a custom authorizer, which basically means that your client will get an identity from an identity provider, and then it will invoke API Gateway with a token or something that the identity provider provided. And before API Gateway invokes the Lambda function, it will invoke another Lambda authorizer that will check the header, will maybe invoke some APIs or check another database to make sure the user is authenticated, is authorized to go on. And then it will return a policy, and API Gateway, based on that result, will go on and invoke your Lambda function. So you can even integrate custom SAML providers or implement your own custom logic there. and you can centralize that for all your APIs in one place. So I think it's a good solution for that. Let's get into the data processing in the real-time world for a few minutes. This is the second category. So we have 4 services. Today we talk about 3 of them. It's the Kinesis family, I call it. So let's talk about Kinesis Data Stream, Data Firehose, and Data Analytics for a few minutes. So Kinesis Data Firehose gives you what we call a data ingestion for free. No, it's not free, but if you count the lines of code that you need to do data ingestion, to bring your data in and to store it into multiple destinations, that's basically 0 lines of code. So for me as a developer, that's free. And then it's very serverless because you don't pay by the hour. It's not a database. It's not a server. You pay by how much data is passing through. So again, low use case, infrequent, startup, new feature. It's very, very cheap, and then it scales linearly with the load, so very serverless friendly. And what happens with Firehose is that you have your record producers that put data in, and what Firehose will do is that you can configure it to write to Amazon S3 or Redshift or Elasticsearch, and again, 0 lines of code to be written here. And even more powerful is that you can map a Lambda function to it that will process or validate or enrich the records that are passing by. So potentially reading from another database if you want, but the power here is that Firehose will buffer the data for a while. You can specify how long or how much data, and Lambda is able to enrich or manipulate or even discard some records if you need to. And then after a while, it gets written automatically to S3, and you can enable compression or other advanced functionalities. If you want to do exactly the same in a RESTful way, using an API instead of using the Firehose put record API invocation, you can put an API gateway in front of it, or you can even put a CloudFront distribution and do exactly the same with Lambda at edge. So you do this at the edge without any central server or any regional API at all. So for the user, for the final user, it's super fast. Or if you have IoT devices, or if you have other applications that need to ingest a lot of data periodically, this will be faster, for example. A few best practices. Well, you can specify a buffer size and a buffer interval. So how much data or how much time need to pass before Kinesis writes the data. And you can optimize that based on how much real time you want your application to be. You can enable compression, and that's a checkbox. You can enable Parquet format if you want to optimize for columnar queries, and that's also a checkbox. Pretty cool. Eventually, you can even say, hey, just also save the raw records here, because maybe you want to replay those records in another test account, or because you want to be able to replay it if anything goes wrong down your pipeline. So that's good to have. Let's talk about another service. It's Kinesis Data Streams. So streams came before Firehose, and Firehose was born because a lot of people were using streams with Lambda behind it to write into S3. So Kinesis solves that problem. You don't have to write that code anymore. But if you have another use case where you have streaming data coming and you want a Lambda processor that does something else with other services or that's doing aggregation and stuff, you can still use data streams. And this is partially serverless because there is still the concept of shards. Okay, the number of shards that you specify on Kinesis data streams roughly corresponds to a server concept, in my opinion. And even if you can auto-scale that, it still means that you have to do capacity planning. And based on the throughput, based on how much data you want to pass through per second, you can estimate how many shards you need. And you can even specify how many batch at the time your function will process downhill. So you can say, my function will process, 100 records at a time in a batch fashion. So even if there are like 200 records per second, your function is given 100, and then it processes them, and then it will take another 100 and go on like that forever. Sometimes you need more throughput. So if there are 200 events per second, but you can only process 100 for some other reason, you want to be a bit faster than that, because otherwise your real-time application is not really real-time anymore, because it takes you more time to process than the data that's coming into the system. So a lot of customers are using this Fanout pattern. So they fetch the data from the stream, and instead of processing it right there with that first function here, they use this as a dispatcher function to invoke other second level kind of functions that will actually process the data. So it allows you to increase the throughput. For example, this is another very useful Fanout pattern in general. There is even a library that does that for you, basically zero code again. Let's talk about real-time analysis. So there is this third service that we call Kinesis Data Analytics. And instead of giving you a Lambda function for each and every record, basically you can write a SQL query in this Kinesis Data Analytics application. So it will receive the data from another stream. Here you write some Java or some SQL that will do aggregation, windowing, all sort of manipulation in a very intuitive way, I think. It's basically SQL. And then the result, after the processing has been computed, can go to a Lambda function or another stream. You can do all sort of things. So imagine that you have devices putting records like the temperature in a room, and you want to make sure that the average temperature is not above or below a threshold in real time, so that you can do alarming, for example. You can have here an average kind of aggregation, and then you pass the average to the Lambda function, and Lambda can just do if average above 25, okay, send an SNS push notification to the operation guy, so they will fix it. There is something probably wrong, and maybe it's also store the historical value there, so we have a time series of values, aggregated averages. So you can do this stuff very easily, and this is what a SQL query looks like. You can do the same in a Java syntax, but I think SQL is a bit more understandable for everybody. And it's super interesting that you can specify this kind of step window here. In this case, it's a 10-minute window, but you can have a 10-second window or a 30 seconds window if you want. So with this 10-minute window here, we are doing a sum or a count or an average or all sort of aggregations. And then the result will be given to our Lambda function downhill that will do some actual logic on it. Cool. Let's go to the next category, which is data lakes. Okay, who knows what a data lake is today? It's kind of a new, strange thing. But if you're used to the data warehousing concept, the idea of doing data analysis, extracting information, building reports, this is a similar solution, but different, slightly different approach. So the idea is the same. We want to collect, consume, analyze, catalog data. But the advantage is that you can put in not only structured data, but also semi-structured and even unstructured data. Most of the power of this approach comes from the benefit of decoupling the compute part of the system and the storage part of the system, so that if you need to run more powerful queries, okay, that can scale in an autonomous way with respect to the storage. It's completely decoupled. Ingestion should be quick and fast and automated, and this is the second biggest advantage. You define the schema of the data not when you need to write, like in the typical database or data warehouse. You define the schema when you go and read it, so much later afterwards. So this has the advantage of making the ingestion faster, and it gives you the advantage of being able to process the data and aggregate and catalog the data in the meantime from ingestion to analytics. So this is a complementary concept to data warehouses. They can live together. There is actually a service that we call Amazon Redshift Spectrum that gives you Redshift data warehouse with the power of the data lake, so that you can have some tables which are real data warehouse and some tables that are maybe stored on S3, and you do a data lake kind of query on those tables. So everything is around S3 on data lakes on AWS. And then you have all the other services and the functionalities around it. So we already saw how you can use, for example, Kinesis Firos to write your data into S3 without writing any code at all. And then you can have like your catalog using Glue and Elasticsearch. You can do all sort of processing using services like Athena or even Lambda if you want. And then all the security auditing using like IAM, KMS for encryption, and Macy for like anonymizing data if you have to be GDPR compliant, for example. Let's get into one of these analysis services. So we call it Amazon Athena, or you can use Redshift Spectrum. It's basically the same, but Spectrum kind of integrates with your traditional data warehouse a bit differently. So what typically happens is that you have data on S3, you want to have your we call them Glue. Glue is a service that does catalogs data for you. So you say, hey, go and discover the data, and based on the pattern, based on the schema hints that you may provide, it will go and create these virtual tables for you. So once you have these virtual tables created, and there is no data movement, no data ingestion after the first ingestion, it's not a database. You can just say, hey, Athena, run this SQL statement on my virtual table. And Athena is based on Presto, and it will just go and find all the objects and distribute the computation. So there is basically a cluster that we handle for you, and it's super powerful because you don't have to take care of, oh, there's not enough storage anymore, or, oh, this query is too slow, add more servers. None of that. We take care of that for you. We scale the computation to as many machines as needed, and all you pay for is not the cluster, is not how many machines, it is how much data your query is scanning. So it's pretty powerful, different approach to analytics, if you think about it, because you don't have this server running 24/7 waiting for queries, and you're paying for idle. You only pay for the queries, and you have a very good reason to optimize your queries, because if they optimize how much data they are scanning, you make them faster and cheaper at the same time. So I think that's a a very useful circle. So let's look at the query. So there is a simple query working on the n-grams table. It's roughly, I don't know, almost 170 gigabytes of data. So it does some where, some grouping, some ordering. I would expect it to take a few seconds, max a minute, I would say, even though it's a pretty big data set. So the query duration might be around 40, 45 seconds. And since I'm scanning 170 gigabytes, I'm paying around 85 cents for it. Because the pricing model of Athena is that you pay $5 per terabyte scanned every month. And if I can optimize this query with partitions and just scan a subset of the data, or maybe with columnar formats, so that I only read specific columns, I only scan a subset of the data, I can make it run faster and cheaper as well. So the best practice here is to use partitions. Is to, for example, if you define year equal 2018 or field equal value in your S3 structure, Athena will automatically recognize those partitions and optimize your queries. So if I query where year equal 2018, it will just read that folder, that subset of the data, and be much faster. If you want to do MapReduce on AWS using Lambda, there is actually a project called PyRen. And PyRen is developed by the guys at the University of Berkeley in California. And they build a system where you can do hundreds and hundreds of teraflops. Like with the standard default, they are up to 10 teraflops of compute. But you can scale as much as you want if you raise the limits. And it's open source. You can check it out. It's pyren.io. Let's quickly get into the last category. I think we have only a few minutes for questions. Machine learning. So how many of you are doing machine learning today? If you're not, I think you should start this weekend. It's a very good opportunity. There is a full set of services that we call the AI services in our AI suite that do not require any machine learning experience. As a developer, all you need to care about is that they have an API that you can invoke. And they will find objects in an image, they will create audio given text, or the opposite, or they will create a chatbot for you. So why not using them? It's an API call away, and you don't need any machine learning experience. So let's see how we can use these services in a serverless architecture, with a serverless architecture mindset. So for example, imagine you have an application that allows users to upload images. So we will store the image on S3 somewhere. And since Lambda is all about having this event-driven API, we can invoke a Lambda function when something happens in the system. So new file on S3, API, Lambda invocation. And maybe we want to run a sophisticated state machine using AWS step functions like the visual one that I showed you before. And in each branch in parallel of the state machine, we want to use the object detection, face detection, moderation detection, and text detection features of Amazon Rekognition, which will deal with images for you. And then at the end, you want to store all the output of these different API calls into S3 or Dynamo or Elasticsearch and allow your same users to search those images using the metadata, using the objects in those images, for example. Let's look at another solution. This is for multimedia objects in general. So let's imagine you have a website that allows your users to upload videos. Okay, you can trigger a Lambda and a state machine on upload in a very event-driven way. And then in parallel, if it's a video or if it's audio, whatever it is, you can detect objects and faces and motion in this image, or you can change the encoding, you can resize it, or you can make different versions with different formats for different devices. Or maybe in parallel, you can take the audio part of the video and transcribe it, and then with Amazon Transcribe, and then understand what's being said, what are the concepts, what's the emotion, what's the key phrases in that sentence using Comprehend. And then you take all this data that you have aggregated in parallel, and maybe you store it on S3 or on Elasticsearch, for example. And to the same users here, you can provide them an API to search those media files. So that's a media solution, super serverless. The only component here is Elasticsearch. That is not 100% serverless because there is still some cluster there, and you have to take care of those servers. But the rest is very event-driven and serverless. And you can just deploy this with one click in your account. It's on the website. Who knows Amazon Connect? It's a fairly new service. It's basically a serverless contact center. It allows you to have your agents speak to people and record conversations and analyze conversations with analytical functionalities. So for example, instead of having agents, you might have an Amazon Connect contact center backed by Amazon Lex, which is our conversational interfaces chatbot service. So let's say these customers want to change an appointment time. So we will just send a text or a vocal message to Connect, and Connect will pass it to Lex, and Lex will analyze the text and the audio, will transcribe it if needed, and will find the information like what time and where and who is the doctor and blah, blah, blah. And then we'll pass all the information to Lambda, and Lambda will change the data in the database and maybe send an SMS back to the customer. So yeah, your appointment is now changed. So you can do all of this serverless, and you don't even need a human operator. Another use case where you have operators instead. So you have customers and agents, operators talking to each other, and you want to extract some information. So you can have your contact trace records, like everything that happened, all the different records about the calls, and you use Pyros to save those into S3, for example. Or in parallel, you may want to take all the recordings and do the same. So you transcribe them and save the transcript into Amazon S3. And then in parallel, you can do comprehension, sentiment analysis, or key phrases extraction. And then you have all this stuff on S3 in virtual tables, and you can query, analyze, and visualize this data. So this is a serverless data contact center solution with real-time analysis. Maybe you can build a dashboard using Amazon QuickSight or serverless query on it using Amazon Athena, and you can merge and join all these different virtual tables in your data lake. So it's a data lake for machine learning using AI services and serverless. It's a bunch of buzzwords in there, but I think it's super powerful. That's all I had for you today. I'm slightly late, and now it's your time to go and build something awesome with this stuff. Thank you, everybody. I think we have another couple of minutes for questions, so I can take maybe 2 or 3. Do you have any questions? We have a question in here. Can we have a mic? If you have any other question that we cannot cover, I'll be around here or maybe in the expo area for another half an hour. Here we go.
Yeah. Great talk, first of all. At the beginning, you have mentioned the cold and warm start of Lambdas.
Yep.
So I wanted to ask you, did you ever encounter an architecture where a high requirement was to have a warm start? And how would you actually implement that?
So if I understand the question is, OK, cold start, how do you go around the problem? How do you fix this problem?
Right.
So especially if you're using Java, as I mentioned before, and very heavy frameworks, or especially if you have to put your functions into an Amazon VPC because you have to read from a database. OK, right now there is a pretty significant cold start, I would say, up to seconds. OK, that's not ideal. But I can tell you, and we pre-announced this in November, few months ago that this is a solved problem. Okay, basically what happens right now is that we need to attach an Amazon ENI, an Elastic something interface into your VPC, and that we do that at execution time. Okay, what will change is that we are able to do that at deployment time, so that all the cold start that needs to happen at execution time completely disappears. And the other thing that will happen is that we will be able to use multiple IP addresses in your VPC for multiple function executions. Sorry, one IP address for multiple function executions. So we solved two problems at once. And a few months ago, we pre-announced it saying a few months. I don't have a date for you, but it's basically a solved problem.
Okay, thank you.
Thanks for your question. Any other question? I have 8 seconds, so probably not. So thank you, everybody, again, and I'll be around all day. Thanks.